Welcome, everybody. It's my pleasure to introduce Woojin Kim from Ohio State University and now moving to Duke University. And he'll be speaking on spatiotemporal persistent homology for dynamic metric spaces. Thanks, Woojin.
Thank you, Henley, for introduction. And thank you for organizing this nice conference. Yeah, today I'm going to talk about persistent homology framework for the study of dynamic metric spaces. This is a joint work with Facundo Memoli, and our work is supported by NSF grant. So one motivation of this study is topological study of collective behaviors. As you already know, there are many instances of collective behaviors in nature, a scrub of fish, a flock of birds, or a swarm of bees. Given such collective behaviors, because the distances between entities change over time, we can see them as dynamic metric data. So as you can see from the pictures, there are lots of interesting geometry and topology going on. So it's kind of natural to adopt TDA ideas for the study of those behaviors. And recently, there are really researchers studied applying TDA idea for the study of collective behaviors or swarming behaviors. These are just several samples from many more works. So all this work used persistent homology idea for the study of time-varying point clouds or swarming behaviors. So the goal of this talk is to build persistent homology framework for dynamic metric spaces. Remember that collective behaviors, such as flocking of birds, can be modeled as a dynamic metric space that I'm going to define more precisely later on. So the question is, how can we quantify the behavior difference between dynamic metric spaces so that we can classify them in a systematic way? And the second question is, how can you summarize multi-scale topological features of a dynamic metric space? As many of you already know, these sort of questions have been well addressed in the setting of static metric spaces. Suppose that we are given a data set which is given as a metric space, which looks like this. Then in the typical persistent homology framework, we build an increasing family of simplicial complexes along the scale parameter axis. Then this example illustrates specifically the Biot-Rips Rips filtration. At each delta, we associate delta Rips complex of the metric space, which consists of all subsets A of X, such that for every pair of points, the distance between them does not exceed delta. And note that not only does each delta correspond to delta Rips complex, but also each pair of delta and delta prime, there is an associated inclusion map between the corresponding Rips complexes. Now, by applying homology functor to this entire filtration, we obtain the so-called Rips persistent homology of a metric space. Then one fundamental theorem in topological analysis is that we can represent this persistent homology as a so-called barcode or persistent diagram. Zeroth homology barcodes encodes multi-scale clustering features of the given data, and the first homology barcode encodes the loop-like structures in the data set, and the second barcode captures the void structures in the data set, and so on. And in general, long intervals in the barcodes are considered important topological features of the data set, whereas short intervals are in general considered less important, or they are artifacts of the noise of the data. So another important theorem in topological analysis is that this summarization process from metric spaces into Rips persistent homology or Rips persistent diagram is stable. So to be precise, there is a dissimilarity measure between metric spaces, the so-called Gromov house of distance. And there is also a notion of interleaving distance on collection of persistent homologies or persistent diagrams. Equivalently, the bottleneck distance can be located here. Then this theorem says that 2 times of the Gromov house of distance between any 2 totally bounded metric spaces is an upper bound for the interleaving distance between corresponding Rips persistent homologies. An implication is that this summarization mapping is stable under perturbations of the input metric data. And another computational remark is that computing this interleaving distance is much more easier than computing the Gromov house of distance between metric spaces. Therefore, we often make use of integrating distance and persistent homology to classify data sets given as metric spaces in applications. So the goal of my talk is to extend this stability theorem to the dynamic setting. So what you're going to do is to define the notion of dynamic metric space, a mathematical model for collective behaviors. And then we are going to define spatiotemporal persistent homology of a dynamic metric space, which is a multi-parameter persistent homology. And we are going to define a metric on the collection of dynamic metric spaces, which is a generalization of the Gromov house of distance. Then this theorem says that summarizing a dynamic metric space into the spatiotemporal persistent homology of the dynamic metric space is stable as before. So let's begin with the definition of dynamic metric spaces. So a dynamic metric space is a pair of a finite set and time-dependent distance functions. It is a function from r cross x to non-negative real, such that whenever we fix a time, the function becomes a metric or pseudo-metric on the underlying set x. And for every pair of points, the distance changes continuously over time. And whenever we pick two different points in the underlying set, the distance between them is not identically zero. The third item is simply because we do not want to have redundant point in the data set. One implicit thing in our definition is that each element in the underlying set keeps each one identity over time. Examples include dynamic point clouds in Euclidean space or any metric space, where each point has a name on it. And trivial examples include constant dynamic metric spaces that are not dynamic, actually. Now we are ready to define the spatiotemporal persistent homology of a dynamic metric space. Remember that now we have two variables, time and scale. Therefore, given a dynamic metric space, it is natural to consider time cross scale parameter space. However, let's observe the following. Let's fix two time t1 and t2, and we consider delta Rips complex corresponding to time t1 and delta prime Rips complex corresponding to time t2. Then, because we have different metrics at different times, we do not have necessarily this containment relationship, right? What we know is whenever we fix time, as the scale parameter grows, we have a larger and larger simplicial complexes. Therefore, using this parameter space, we do not obtain functoriality with respect to the time parameter. Therefore, we change our perspectives about times. We consider the collection of time intervals instead of considering timeline. By int, let me denote the collection of all closed time intervals. We can graphically represent this collection as the upper half plane above the diagonal line. So the point t1, t2 above the diagonal line corresponds to the closed time interval t1, t2. And then whenever we have two closed time intervals, the one corresponding to the larger one is located at the upper left of the point corresponding to the smaller one. Now let's keep this diagram in mind and let's put this in the three-dimensional space, xy plane in the xyz space. And we are going to define spatiotemporal Rips filtration now. Let's fix a certain time interval I. Then at the height delta, we associate delta Rips complex over the underlying set x, where the distance function is the minimum distance over the time interval I. Namely, it consists of all subsets A of x, such that every pair of points in A, there must be a moment in the time interval I such that the distance between entities is less than or equal to delta. Now let's fix another time interval I prime, which contains I, and let's fix another delta prime, which is greater than or equal to delta. Then the Rips complex corresponding to I comma delta is contained in the Rips complex corresponding to I prime comma delta prime. The reason is because the distance function corresponding to the larger one is smaller than the distance function corresponding to the smaller interval. So Graphically, we can say like this: if my point in parameter space moves left, back, or upward direction, our simplicial complex gets bigger. Therefore, we can see this picture as the three-dimensional simplicial filtration out of dynamic metric space. Now, by applying homology functor to this filtration, we obtain the spatiotemporal Cartesian homology over dynamic metric space. One remark is that if gamma x is a constant at static metric space x dx, then this spatiotemporal Cartesian homology is constant with respect to the time factor int. Therefore, if you want, you can discard this first factor and reduce this three-dimensional filtration to the vertical one-dimensional filtration. Also, if we have two constant dynamic metric spaces, gamma x is constant at x dx and gamma y is constant at y dy, then the interleaving distance between these multi-parameter Cartesian homologies is actually coincides with the interleaving distance between standard ripped Cartesian homology of static metric spaces. Let me try to illustrate which topological features are considered important in our framework. So for comparison, let's look back the setting of static metric spaces first. Suppose that we would like to compute the interleaving distance between first Ripp's Cartesian homology over one point space and first Ripp's Cartesian homology of x dx. Then we know that one point space has no one-dimensional homological feature. Therefore, this Cartesian module is going to be trivial. And we can regard this value in the pink box as somehow a norm of one-dimensional Cartesian homology of x dx. And if you imagine if you think about it a little bit, then it's not hard to check that this value is large only when this metric space contains a large circular configuration. That means that a large topological features are regarded as significant in the standard framework of Cartesian homology. Now let's consider a similar situation in the dynamic setting. We would like to compute the spatiotemporal Cartesian homology of a one-point space and spatiotemporal Cartesian homology of a given dynamic metric space, gamma x. Then it is not hard to check that this value is large only when gamma x contains some large circular configuration which persists for a long time. Therefore, we can conclude that large topological features which persist a long time are the significant features for dynamic metric spaces. And the same principle holds for other dimensions. For example, if we replace this one-dimension homology by zeroth homology, then you can check that this corresponding value can be large only when gamma x contains at least two subclusters which are forward to each other, and this state persists for a long time. Now we are ready to define the distance between dynamic metric spaces. One natural distance we can consider is to integrate the Gromov house of distance against the timeline. However, sometimes that distance is not discriminate enough, as we will see in the following example. Let's consider these two dynamic metric spaces. The first one consists of 3 points. 2 points of them are fixed at -1 and 1 on the real line, and the middle one has time-dependent coordinate sin of t. This middle one oscillates between -1 and 1. And the other DMS is almost the same, but this middle one has a little bit different description. This middle one oscillates between the origin and the point located at 1. Then one observation is that whenever we fix a time, these two fixed metric spaces are isometric, right? Sometimes they have exactly the same picture, and sometimes one is obtained by reflecting the other with respect to the origin. Therefore, if we integrate the Gromov house of distance against the time, then we obtain 0. Therefore, integration of the Gromov house of distance cannot discriminate these two dynamic metric spaces. And if you remember the standard stability theorem, this interleaving distance between Ripp's Cartesian homologies is upper bounded by 2 times of the Gromov house of distance. Therefore, the integrand of this integral is also 0. So integration is going to be 0. Therefore, integration of the interleaving distance is not discriminating these two dynamic metric spaces. Now, let me introduce a notion of strong isomorphism between dynamic metric spaces. Two dynamic metric spaces, gamma x and gamma y, are called strong isomorphic if there exists a bijection between the underlying set such that for all time, this bijection serves as an isometry. So here's a known example. These two dynamic metric spaces are time-wisely isometric. However, you cannot find any bijection between the underlying set, which serves as an isometry for the entire timeline. Now, we want a metric which discriminates weakly isomorphic dynamic metric spaces, time-wisely isomorphic dynamic metric spaces. So to say the conclusion, actually, we are going to introduce the so-called interleaving distance between dynamic metric spaces. It is defined as the infimum of epsilon for which gamma x and gamma y are epsilon interleaved. What do I mean by epsilon interleaved? That means that there exists a correspondence between sets x and y. A correspondence is nothing but a relation between sets x and y. When we project this R to the first vector, it must cover the entire x. And when we project down this R to the second vector, it must cover the entire y. And it must satisfy the following condition. For every time, for every pair xy, x prime, y prime in R, the distance between y and y prime at time t should be an upper bound for the minimum distance between the point x and x prime over the time interval from t minus epsilon to t plus epsilon up to 2 epsilon slab. We also require a symmetric condition of this by interchanging the role of x and y. Let me explain again using the picture. Let's fix two entities in gamma x and we look at the corresponding element by R. And at time t, we measure the distance between these two entities in gamma y. It must be an upper bound of the minimum distance between the corresponding entities over the time interval from t minus epsilon to t plus epsilon up to 2 epsilon slab. And the symmetric condition of this. Then one remark is that if epsilon prime is larger than epsilon, and if gamma x and gamma y are epsilon interleaved, then gamma x and gamma y are epsilon prime interleaved as well. Therefore, defining our interleaving distance as the infimum of epsilon for which gamma x and gamma y are epsilon interleaved is natural. Another remark is that if gamma x and gamma y are constant dynamic metric spaces, constant at x dx and y dy, then this interleaving distance between dynamic metric spaces coincides with the Gromov-Hausdorff distance between the corresponding static metric spaces. The reason is not difficult to check. So remember that this was a condition we saw in the previous slide. If gamma x and gamma y are constant dynamic metric spaces, we can get rid of all these time-relevant terms, these colorful things. Then we end up with this simpler condition. For every pair xy, x prime, y prime in R, the distance difference is upper bounded by 2 epsilon. And this is exactly the condition we need to claim that the Gromov-Hausdorff distance is upper bounded by epsilon. Now, let's consider the collection of all bounded dynamic metric spaces. A dynamic metric space is bounded if there exists a constant m such that the distance function never exceeds m. Then indeed, the function we defined in the previous slide is a metric on the collection of bounded dynamic metric spaces. It is not an extended metric. It is not a pseudo-metric up to strong isomorphism. That means that this metric can discriminate these two weakly isomorphic dynamic metric spaces. I would like to also again emphasize that our theorem reduces to the standard theorem when we restrict ourselves to the constant dynamic metric spaces. So let's consider some computational aspects of our framework. Remember that we wanted to use our metrics, interleaving distance between dynamic metric spaces or interleaving distance between spatiotemporal Hessian homology to classify a collection of collective behaviors or collection of dynamic metric spaces. However, unfortunately, both of distances are harder to compute. the interleaving distance between multi-parameter Gaussian homology is known to be NP-hard to compute in general. And remember that this interleaving distance between dynamic metric spaces was a generalization of the Gromov-Hausdorff distance, but computing Gromov-Hausdorff distance is already known to be NP-hard, therefore it is NP-hard to compute. So what we do in our paper is that we find another lower bound for this left-hand side again, utilizing the dimension function for the zeroth spatiotemporal Gaussian homology and rank invariant for the higher dimensional Gaussian homology. And we use a slight generalization of the Patel's erosion distance to compare those invariants. And that lower bound is polytime computable and kind of good enough to discriminate these two dynamic metric spaces. So we are happy about those framework. So let me introduce an experiment we carried out using this spatiotemporal Gaussian homology. We classified simulated blocking behaviors using our framework. So this experiment was carried out with Nate Close and Jane Smith, who are PhD students at Ohio State and University of Minnesota, respectively. For doing that, we used the so-called void simulation. Let me show you the simulation briefly. So that simulation is controlled by a few different parameters. So you can change the number of entities, and if you increase separation parameter, they tend to be separated. And if you increase cohesion parameter, they try to be cohesive to each other. And if you increase alignment parameter, they try to be aligned with their neighbors. So by tuning these parameters, we identified 5 different swarming behaviors. And for each parameter setting, we repeated simulation 100 times with random initial configurations. We computed zeroth spatiotemporal Gaussian homology and dimension function of it. And we computed the 505 erosion distance matrix among those things. And we carried out hierarchical clustering and MDS plotting. And the details of this experiment are available on this website. And the result was very nice. These 5 different colors stand for 5 different parameter settings, and each color has 100 behaviors. And this is the result of hierarchical clustering, and this is the result of MDS plotting. By the way, these results are mainly produced by this Nate. He did all the nitty-gritty things about this experiment. I'd like to note that. And summary, we defined spatiotemporal Rips filtration for dynamic metric space, which is stable with respect to the metric we introduced on the dynamic metric spaces. And in particular, our stability theorem was a generalization of the standard stability result among static metric spaces. And I also briefly introduced our classification experiment. And here are the references and some other references, images and videos from Robert Crest and Kei Tarayama PhD thesis, and some YouTube video. Thank you for paying attention.
Fantastic. Thank you so much, Woojin. Before we get to questions, let's briefly unmute yourself and applaud, and then mute yourself again, please.
Thank you.
Questions for Woojin? Yes, Daniel?
Hey, thank you. That was great. I just had I know you were getting a little rushed at the end. I just had a question about what you could conclude from the analysis of the distances in the end. I mean, it looked a little bit like you were doing sort of a recovery experiment to say, well, we know that these flocks have these parameters, and so you know, can we sort of get back that we classify behaviors into distinct groups as we know we set them? What was there more to it than that, or more that you wanted to say about it than that?
Sorry, I did not understand your question. Can you repeat the question, the last part?
Yeah, just was there more that you were trying to show, maybe that you just didn't have time for?
No, this is actually the end of the result. We were just wondering whether we can classify these dynamic spaces as we expected. But I know that using this sort of idea, there are many interesting applications we can make use of this idea. For instance, work by Ulmer, Jagan-Meyer, and Topaz, they used Partial homology to test the validity of a mathematical model for collective behaviors. For doing that, we need some sort of metric. And so this sort of idea can be used for like those kind of applications. But we didn't do that application yet. Yeah.
Cool, thank you.
Does this answer your question?
Yeah.
Yeah.
Further questions? Woojin, I had a quick question. So, you know, Gromov Hausdorff distances are actually a metric on, you know, maybe the set of compact metric spaces, something like that. In the dynamic setting, you have the bounded hypothesis.
Right.
You don't need a compact hypothesis? Like, what if you look at the reals and the rationals?
No, we remember that our dynamic metric space was just finite.
I see.
Finite, we are just considering finite metric spaces, right?
I see.
Right. Yeah.
Okay. And do your dynamic metric spaces have any sort of continuity in time? Like they sort of move, like the distance?
Yes.
I see.
Right. That was in the definition of dynamic metric space. In the second bullet point in that definition, we required that for each pair of entity, the distance between them changes continuously over time, right? That requires that, that means that this dynamic metric space can be seen as a continuous curve in the Gromov-Hausdorff space.
Right.
Yeah.
Thanks.
Yeah, thanks.